Okay, so we have a quantum physics of matter practice final exam, first year graduate level. So let's begin. This is part one. A particle of mass m moves in the one-dimensional potential v of x given negative v naught, comma, absolute value of x is less than a, and 0, absolute value of x is greater than or equal to a. Okay, for part A, derive the transcendental equations governing the even and odd parity bound states. Part B, show explicitly that there is always at least one bound state in one dimension. Part C, obtain the approximate ground state energy in the limit v naught a squared is much larger than h bar squared over 2m. And part D, discuss qualitatively how the number of bound states changes as v naught and a vary. So I'm going to go through these at a relatively quick pace so you have them as a reference. I'm going to go over the derivation on the second page. I'm just going to get through the A through D in a condensed form first. So for bound states, negative v naught is less than e is less than 0. We define there our k or kappa equals square root of 2m times the quantity e plus v naught over h bar. Alpha is square root of negative 2m e over h bar. Inside the well, the wave function is sinusoidal. Outside, it decays exponentially. For even states, you're going to get psi is a cosine kappa x. Some people use k. Inside the well, matching psi and psi prime at x equals a gives k tangent of ka equals alpha. Okay, I'll use that interchangeably. You could use k or kappa for those. Depends, even though, depends on who's writing it. For odd states, psi equals a sine of kx. So matching here, we'll keep this in terms of k. So it gives a negative k cotangent of ka equals alpha. Thus, the allowed energies are determined by k tangent of ka equals alpha, and negative k cotangent of ka equals alpha. There's always at least one bound state in a one-dimensional attractive well, because even an arbitrarily weak attractive potential lowers the energy below the continuum threshold. For a deep well, v naught a squared is much larger than h bar squared over 2m. The ground state is close to the infinite well result for a box of width 2a. Shifted downward by negative v naught. E naught is approximately negative v naught plus h bar squared pi squared over 8ma squared. So the number of bound states increases as either v naught or a increases. Okay, so just building on that, if we go back to part A, the derivation of the transcendental equations, let's just go over this in a bit more detail. Okay, so here, derivation for a, inside we have absolute value of x is less than a, and that would be negative, we're going to use a negative h bar squared over 2m psi double prime minus v naught psi equals e psi. And then we have psi double prime plus k squared psi equals 0. K equals square root of 2m times the quantity e plus v naught over h prime. Outside, absolute value of x is greater than a. We get negative h bar squared over 2m psi double prime is equal to e psi. Now for bound states, e is less than 0, so psi double prime minus alpha squared psi equals 0. So alpha is going to equal negative square root of negative 2me over h bar. Normalizability requires the outside wave function to decay. Psi sub out equals b e to the negative alpha x, where x is greater than a. Okay, so now we go to the states. The even state, psi sub n equals a cosine of kx, continuity at x equals a cosine ka equals be negative alpha to the negative alpha a. Derivative continuity, negative ak sine of ka equals negative alpha be to the negative alpha a. Now we divide here, set up this proportion, negative a k sine of ka over a cosine ka equals negative alpha b e to the negative alpha a over b e to the negative alpha a. Solving here, negative k tan of ka equals negative alpha, so k tan of ka equals alpha. Okay, and the odd state psi sub n equals a sine of kx. Continuity, a sine of ka equals be, negative alpha times a. Our derivative continuity is going to be ak cosine of ka equals negative alpha be to the negative alpha a. And we divide and we get now k cotangent of ka equals negative alpha. So negative k cotangent of ka equals alpha. Okay, so that's for number 1, and we can now move along to number 2. Okay, so number 2. Okay, consider a particle with energy E is less than V naught incident on the rectangular barrier given. Here with this piecewise function V of x. Part A, derive the transmission coefficient T of E. Part B, show that in the thick barrier limit, here definitely we'll call it kappa. Kappa L is much greater than 1. The transmission probability becomes exponentially suppressed. Part C, a scanning tunneling microscope relies on tunneling through a vacuum gap. Explain quantitatively why the tunneling current is highly sensitive to chip distance. And part D, estimate the fractional change in transmission of the barrier with the width changes by 0.1 nm. Okay, so quantum tunneling through a barrier. We'll do something similar than we did with what we did with number 1. We're going to go through the basis, the condensed version of these first, and then I'll go on the second page with the a little bit more in detail with the derivation of the transmission coefficient. Okay, so here we go here. For E is less than V naught, kappa is going to equal square root of 2m times the quantity V naught minus E over h bar. So the transmission coefficient for the rectangular barrier is this, T equals 1, plus the quantity V naught squared, hyperbolic sine squared of kappa L over 4E times the quantity V naught minus E, and that is inverse, it's raised to negative 1. Okay, raised to negative 1. And for a thick barrier now, kappa L is much greater than 1. Hyperbolic sine squared of kappa L is about 1/4 E to the 2 kappa L. Therefore, our T is about 16E times the quantity V naught minus E over V naught squared times E to the negative 2 kappa L. So we get T is proportional to E to the negative 2 kappa L. And we'll go over that on the second page more in detail with the intermediary steps there. Now we could say, just moving along from what we read up here for BCD, so this explains why STM current is extremely sensitive to distance. If L changes by delta L, then T sub nu over T sub old equals E to the negative 2 kappa change delta L. For a typical vacuum barrier, we get this relationship between kappa, okay, and that 1A here, negative 1, and then if delta L equals 0.1 nm, we get that 1A. So T sub nu over T sub old is negative E to the negative 2, which is 0.135. So increasing the gap by 0.1 nm reduces transmission by about 86.5%. In general, if I talk too fast, sorry about that if I mispronounce a variable here and there. Just trying to get through this quickly so you have it as a reference. But let's go now to the real important part. All of this is important, but the important part, the derivation of the transmission coefficient. So here, this derivation. Okay, so for 0 is less than x is less than L with E is less than V naught. we get negative h bar squared over 2m psi double prime plus v naught psi equals e psi. So psi double prime equals kappa squared psi. Kappa is equal to square root of 2m parentheses times that quantity v naught minus e over h bar. Inside the barrier, psi equals ae to the kappa x plus be to the negative kappa x. The exact, now we get this exact transmission probability is now that. Okay, what we had for t. K, kappa L, product of is much greater than 1. Hyperbolic sine of kappa L is about 1/2 e to the kappa L. Hyperbolic sine squared of kappa L is about 1/4 e to the 2 kappa L. So our t is about v naught squared over 16e times the quantity v naught minus e times e to the 2kl raised to the -1. So just writing that without the -1 exponent, we have t is approximately 16e to the 16e times the quantity v naught minus e over v naught squared times e to the -2 kappa L. Okay, so therefore our t is proportional to e to the -2 kappa L. And just to add to this, if the width changes by delta L, t sub nu over t sub old, that equals -2, that equals e to the -2 kappa times the quantity L plus delta L over e to the -2 kappa L. So this would become e to the -2 kappa delta L. Okay, so that's for number 2. Hopefully I didn't mispronounce much. I know I'm talking fast. I'm on autopilot now. Sorry about that. Okay, so that's 2. Moving along to 3. Whoops, it easy. Okay, so number 3. A one-dimensional quantum harmonic oscillator has Hamiltonian given here. H equals p squared over 2m plus 1/2 m omega squared x squared. So part A, let's see here. Using ladder operations, we want to derive the energy spectrum. Let's see, for part B, we have there computation of bra n x squared ket n and bra n p squared ket n. And we want to now show the coherent states, minimize the Heisenberg uncertainty relation, and perturbation h prime equals lambda x to the 4th is added. Compute the first order correction to the ground state energy. Okay, so we want to define these ladder operations here. A is square root of m omega over 2 h bar times x plus I over the square root of 2m h bar omega p. Canonical stuff here. A dagger equals square root of m omega over 2 h bar times x minus I over square root of 2 m h bar omega times p. Okay. Here, let's see what we have here. Then we have h equals the following: h bar omega times the quantity a dagger a plus 1/2. Therefore, E sub n equals h bar omega times the quantity n plus 1/2. And also we have here x equals square root of h bar over 2 m omega times the quantity a plus a dagger. Okay, so using our ladder operations here, so we have our bra n x squared ket n, that equals h bar over 2 m omega times that quantity 2n plus 1. And here we have the second component of what we want to compute here. That is that bra n p squared, sorry, not squared p squared, oh, n ket, or ket n, okay, equals m h bar omega over 2 times the quantity 2n plus 1. Okay, so here for Heisenberg, for coherent states delta x, delta P equals h bar over 2. So coherent states minimize the uncertainty relation regarding position momentum changes in those. And for the perturbation, h prime equals lambda x to the fourth. The first order ground state energy correction is this. Okay, given right here. For the oscillator ground state, here expectation value of x to the fourth is 3 times h bar over 2m omega squared. Okay, and so, yeah. So E0 first order gets us this 3 lambda h bar squared over 4m squared omega squared. Okay, so that's number 3. And let's see, we can now move on to number 4. Okay. Okay, so number 4, we have two particles have angular momentum given for j sub 1 is 1 and j sub 2 is 1/2. Part A, determine all possible total angular momentum quantum numbers J. For part B, construct the coupled states ket Jm. And let's see, we now have using the Calabish-Gordon coefficients. And then we have for the given state here with J and M, calculate the expectation value of J sub Z, and a weak magnetic field is applied in the Z direction, determine the Zeeman splitting pattern. Okay, so angular momentum and spin coupling. So we're given J sub 1 is 1, J sub 2 is 1/2. So our total possible angular momenta are here. J equals J sub 1 plus J sub 2. Then J sub 1 plus J sub 2 minus 1, and on and on and on. And that's, looks like the pattern there is going to the absolute value of difference between J sub 1, J sub 2. So we could say J is 3/2 and 1/2. Okay, so I'm not going to read all these kets out for the coupled states, but here you go. Here's the coupled states here for our kets. And it's just using what you know about computation with these, and this is what they come out to. Okay, so this is more of a computation problem for each with our kets. Okay, and the J equals 1/2 states, okay, are given here. Okay, so our kets here, and expectation value here of J sub Z, that's going to be M h bar equals h bar over 2. Okie dokie, and here, this is more of a conceptual side of it for letter D. In a weak magnetic field, let's see what we have here. Determine the Zeeman splitting pattern. It's in the Z direction, so in a weak magnetic field, delta E is proportional to MB. Thus, the J multiplet splits into 2J plus 1 levels. For J equals 3/2, there are 4 Zeeman levels. M equals 3/2, 1/2, negative 1/2, and negative 3/2. For J equals 1/2, there are 2 levels. M equals 1/2 and negative 1/2. Okay, so that's for number 4. And now we could move along to number 5. Sorry about that. Okay, so number 5. Okay, so we get 2 identical spin 1/2 fermions occupy a one-dimensional infinite square well. I'll read through all 4 of these. A, B, C, and D. Construct a properly anti-symmetrized spatial spin wave functions for the 2 lowest energy states. Part B, show explicitly how the Pauli exclusion principle emerges. Part C, determine the ground state energy and first excited state energy of the 2-particle system. Part D, compare the result with the case of identical bosons. Okay, so identical particles and exchange symmetry problem. So here's what we could do. Let the well have length L. Single particle energies are epsilon sub n equals n squared pi squared h bar squared over 2ml squared. For 2 spin 1/2 fermions, the total wave function must be antisymmetric under exchange. The ground state, both particles occupy n equals 1. So the spatial part is symmetric, and psi sub s equals phi sub 1, x of 1, x sub 1, phi sub 1, x of 2, x sub 2. Therefore, the spin part must be anti-symmetric. And then here we have chi a equals 1 over that square root of 2. And we have ket up, down, minus that ket down, up. So yeah, that's what we have there. So the ground state is the following. We have the capital psi is phi sub 1, x of 1, phi sub 1, x of 2 over that ket up, down, minus ket down, up over square root of 2. And some people would say up, down, ket minus down, up, ket. Sorry if sometimes I go back and forth between that. Technically, I guess you're supposed to say, yeah, more preferred nomenclature, up, down, ket minus down, up, ket. Alrighty. Now from here, the ground state energy is E naught equals 2 epsilon sub 1 equals pi squared h bar squared over ml squared. The first X-city configuration has one particle and n equals 1, and 1 and equals n, and 1 and n equals 2. And E sub 1 is E sub epsilon sub 1 plus epsilon sub 2, so that's going to equal 5 E sub 1. So E sub 1 equals 5 pi squared h bar squared. Okay, whoops-a-daisy. 5 pi squared h bar squared over 2ml squared. Okay, so here, just expanding on this, the Pauli principle appears because two fermions cannot occupy the same complete quantum state. And for bosons, the total wave function must be symmetric. Two bosons could both occupy n equals 1, so the ground energy is also 2 epsilon sub 1, but no anti-symmetric spin requirement is needed. Okay, so let's see, that is for number 5. Oh yeah, we're ready for number 6. Okay. All right, so number 6 here, let's see, whoops. Okay, so number 6, this says up here, sorry about that. Consider an ideal Bose gas in 3 dimensions. Okay, I'll read all 4 components. Starting from the density of states, derive the Bose-Einstein distribution. Derive the critical temperature T sub C for Bose-Einstein condensation. Show that below T sub C for letter C is n naught over n equals 1 minus the quantity T over T sub C to the 3/2. And D, explain physically why Bose-Einstein condensation does not occur for an ideal classical gas. Okay, so I'm going to go over this in a condensed form, and then we'll go over on the second page part A's derivation of the Bose-Einstein distribution. But Bose-Einstein condensation for bosons here, let's see what we have. We have that's n bar of epsilon equals 1 over e to the beta times quantity e minus mu minus 1. So that's canonical stuff. Very important. The density of states in 3 dimensions is proportional to g of epsilon is proportional to v epsilon to the 1/2. And all this stuff on this practice exam is important. Very, very good to know. The number of excited particles is that n sub ex equals this integral 0 to infinity we have the quantity g of epsilon over e to the beta times the quantity epsilon minus mu, and then minus 1 d epsilon. And at the condensation temperature, as mu approaches 0, we get n equals v times the quantity sorry about that right here, n equals v times the quantity m k sub b t sub c over 2 pi h bar squared to the 3/2 zeta Sorry about my horribly drawn zeta. Zeta of 3 halves. So T sub C equals 2 pi h bar squared over m k sub b times the quantity m over v zeta of 3 halves raised to the 2/3. Below T sub C, n sub ex equals n times T over T sub C to the 3 halves. So n naught over n equals 1 minus T over T sub C to the 3 halves. And lastly here, just for the condensed form of this, a classical gas does not condense because classical particles do not have the Bose enhancement that allows macroscopic occupation of one quantum state. Okay, so let's just now go back to this part A, a derivation of the Bose-Einstein distribution. So I just want to make sure we have a bit more in the explanation for that. So this is that part A. So going on to that. Okay, so the Bose occupation here, we have that n bar of epsilon equals 1 over e to the beta times the quantity e minus epsilon minus mu minus 1, and that condensation u approaching 0. So the excited population n sub ex equals that integral 0 to infinity g of epsilon over e to the beta times epsilon minus 1 d epsilon. For a 3-dimensional ideal gas, g of epsilon is v over 4 pi squared times the quantity 2m over h bar squared to the 3 halves times epsilon to the 1/2. N sub ex equals v over 4 pi squared times the quantity 2m over h bar squared to the 3 halves times the quantity 0, this integral 0 to infinity epsilon to the 1/2 over e to the beta epsilon minus 1 d epsilon. Okay, so what we could do here is we let x equal beta epsilon. Okay, and then we have here epsilon equals k sub b tx, and then d epsilon equals k sub b t dx, e to the 1/2 de equals k sub b t to the 3 halves x to the 1/2 dx. So now n sub ex equals v over 4 pi squared times 2m over h bar squared to the 3 halves times k sub bt to the 3 halves times this integral 0 to infinity, and now this is x to the 1/2 over e to the x minus 1 dx. Okay, so now using this integral here from 0 to infinity, x to the 1/2 over e to the x minus 1 dx, that's going to equal gamma of 3 halves, zeta of 3 halves, and gamma of 3 halves equals square root of pi over 2. So n sub ex equals v times the quantity m k sub bt over 2 pi h bar squared to the 3 halves, zeta times zeta over zeta of 3 halves. Okay, and at t equals t sub c, n equals n sub ex of t sub c, n equals v times the quantity m k sub b t sub c over 2 pi h bar squared to the 3 halves, zeta of 3 halves. Solving for t sub c, excuse me, equals 2 pi h bar squared over m k sub b times quantity n over v, zeta of 3 halves, that quantity raised to the 2/3. And below t sub c, n sub ex of t equals n times the quantity t over t sub c to the 3 halves, n naught equals n minus n sub ex, and n naught over n equals 1 minus t over t sub c to the 3 halves. So that's for number 6, and that's part 1. Part 2 will come next. Thank you.